Hello, I am Junge from the EPFL Create Lab, and today I'll present to you our paper on bio-inspired reflex systems for learning visual information for resilient robotic manipulation. The basis of this paper stems from the fact that humans have a great sense of self-preservation. Largely, we are equipped with two systems in our bodies to deal with this. One is a reactive behavior triggered by the central nervous system. For example, as you can see in this video, when we touch a hot stove, a reflex behavior is triggered. Under this sort of potentially life-harming situations, our body can react very quickly without the brain being involved. The second system is the learned behavior, where we have long-term learning to avoid such situations to minimize the painful experiences. Now, the question is, how do we develop robots to do the same by exploiting its brain and its body? This could be to intelligently react to stimuli, to preserve its life, and also to make safe future decisions. To consider this, we turn back to the human pain reflex system. Starting with this as a template, we can consider the robotic counterpart. In the robotic counterpart, the spinal cord is replaced by analog circuits, which can provide the fast and reactive behavior. The brain can be considered as the microcontroller or a computer, which could run a learning algorithm to capture the contextual information of the environment which caused the painful experiences in the first place, and then use that context to avoid them in the future. To demonstrate this robotic concept, we look at a simplified setup which simulates a scenario of cleaning a kitchen stove. In this setup, the green boxes you can see on the screen represents the waste that needs to be removed off the stove. The stoves themselves can be on or off based on the indicator light, which can be red or white. The objective of this task is to remove all of the cold waste, and in this case, that is the one you can see in the middle and to the right. This process itself is performed automatically using a UR3 arm, as shown here, which is equipped with a gripper that has the pain reflex circuit. The boxes also have Peltier elements, which can become physically hot. The first self-preservation systems is the actual reflex arc, which on the robot is the reflex analog circuit. Under normal circumstances, the robotic hand is controlled by the brain, which is the microcontroller. However, when a hot object comes in contact with the robotic hand, the thermistor provides a signal to the reflex circuit, and then the signal from the microcontroller is overridden to open the gripper as fast as possible. The video here demonstrates the speed of the reflex signal, where when touching hot objects, the gripper opens much quicker than in normal operation. The second self-preservation system is the long-term learning. To do this, we propose an iterative learning approach. In this approach, we iterate through different stove configurations, and throughout the process, we learn from mistakes, or in this case, touching the hot object. We start with a new stove scene with unseen configurations of waste and the stoves. Then we identify the locations of the waste using classical computer vision. In this case, we see two wastes. Then we pass this image through a YOLO v5 network to predict whether the objects themselves are hot. And we see the probability of it being hot through its class label confidences. Based on these class labels, we use an epsilon greedy algorithm, which decides whether or not to grasp the object. Then, when the grasping or not grasping, this action is completed, we iterate through to a new scene. The learning itself happens when we encounter a hot object when grasping. If the reflex circuit was triggered in this scene, then we retrain the YOLO v5 network with the new images and the ground truth labels, which we collect from the gripper. A short summary of the results from the iterative learning process is shown here. The x-axis is the different stove configurations that the robot has gone through. And here, while there are 30 stove configurations, there are only 8 neural network training iterations, since the training only happens when the robot touches 8 hot objects. In the beginning, we see that the network is incorrectly predicting cold objects as hot, as well as their confidences being quite low. Somewhere in the middle, we see an increase in confidence, but we are still seeing false positive across the scene. In the end, at the 8th iterations, the predictions become much more stable. This can be seen as after the 19th stove configuration, there are no more retraining, which means the robot did not encounter a hot object anymore. Finally, to verify whether learning can indeed be applied generally to unseen objects, we use a thought experiment-inspired method to extract the belief of the robot looking at the environment. This is to see whether the robot can learn the contextual information of the environment, whether the environment itself is hot or cold, rather than the object itself. To do this, we start with an empty scene and we generate multiple images of synthetic waste objects that are scattered around. Then, for every image, we run a neural network prediction, and we get an idea of whether that synthetic object would be hot or not. This is very similar to us humans running thought experiments, thinking if there was an object here, would that be hot or cold? Finally, we collate these predictions into a single heat map to generate a visual representation of the robot beliefs. By doing so, we are able to apply this understanding to unseen scenarios and manipulate objects that we have not seen before. In conclusion, this paper presents an embodied approach to designing robots that both react and learn from painful experiences. To extend this work, we can improve the physical intelligence of the robot, such as incorporating self-healing materials, and also to extend learning scenario from this toy problem to other scenarios, such as safe human and robot interactions. This is it, and thank you very much for listening.